In our earlier videos, we have already discussed question 1, 2, 3 and then question 4, 5, 6. In the next video, in this question, we are going to discuss the remaining questions of question paper 42 of 9701 chemistry, that is A-levels chemistry of the examination series May-June 2025. So let's start with question 7 now. So here is question 7a. 2-aminobutane, here is the structure given, exists as a mixture of two enantiomers. Now define enantiomers. So what are the enantiomers? Enantiomers are the compounds, or you can even say isomers, are the compounds or isomers which can rotate the plane of polarized light in equal and opposite direction, that are called the enantiomers. Okay, so question B here is, now let's go ahead. Explain why the aqueous solution of 2-aminobutane has a pH greater than 7 and include an equation in your answer. Now, if it has pH greater than 7, it is obviously basic, and base means it can accept H+. So H+ has to be accepted by 2-aminobutane. Now, the question is, explain why the aqueous solution of 2-aminobutane has a pH greater than 7. That shows that the 2-aminobutane has to be dissolved in water, and that aqueous solution has a pH greater than 7. So we have to show a structure in which it can accept the H+. So, and it's written, include an equation in your answer. Now we know that 2-aminobutane has an amine group which can accept H+. If we write an equation where it accepts an H+, here we know it is NH2, CH2 and CH3. Now if it accepts H+, so we need to show the addition of H+ here. Now the amino part, that is the amine part, is going to accept the H+ because that makes it basic. So if we write that way, CH3CH, then if NH2 accepts H+, it makes it NH3 plus here. So this is how we are going to write it. Or we can even write H2O here in place of H+, because we have to show that the aqueous solution of it is having a pH greater than 8. So we need to show water here, and then CH2, CH3, that is remaining part remains the same. So if now out of H2O, H+ has gone with the amine group, then the remaining part is OH minus. Now why does it has a pH greater than 7, or it is basic in nature? Because the amine group, that is NH2 group accepts H+ from the water, and that's why it acts as a basic substance. The second part is 0.10 mole per dm cube solution of diethylamine. So here is that diethylamine has a higher pH than 0.1 mole per dm cube solution of 2-aminobutane, and this is the simple structure of 2-aminobutane. Suggest why. Now understand diethylamine, what kind of a structure it has. Understand, it is CH3, CH2, NH, and there is another CH2, CH3 group bonded to NH. That is, one of the hydrogen of NH2 is removed and it is replaced by an alkyl group. Now understand, the structure of this is different than this. Let me draw the structure here. CH3CHNH2, that is 2-aminobutane has this structure. So it's not in between the the nitrogen is bonded to two hydrogen here. Understand this difference, but here the nitrogen is bonded to only one hydrogen and two of the bond is occupied by the ethyl group, that is the alkyl groups are bonded to nitrogen directly. Here only one alkyl group is bonded to nitrogen directly in the amine group. That's the difference. So here in the 2-aminobutane there are two hydrogen and one alkyl group, but in diethylamine there is only one hydrogen and two alkyl groups bonded to it. Now if there are two alkyl groups, understand alkyl groups are electron donating, which makes the lone pair of nitrogen more available to bond with H plus, and that makes it more basic, that is it has higher pH. So let's understand, write it that diethylamine have two alkyl groups directly bonded to nitrogen, which are electron donating, or you can even say which has positive inductive effect, that also can be written. This makes lone pair of nitrogen more available to bond with H plus, so it has higher pH than 2-aminobutane, which has only one alkyl group bonded to it. Now this question is a 2-mark question and you have written 2 valid points explaining it, that is there are 2 alkyl groups bonded to it, and that's why which are electron donating makes lone pair more available, or you can also say its electron density of nitrogen increases, that also can be explained. So these 2 valid points are acceptable for 2 marks. The third part is again that diethylamine reacts with the ethanoic acid given here. Complete the equation for this reaction. Now understand, this is an acid-base reaction. Acid-base reaction is going to make a salt. Now in this what happens is the H plus of the acid is accepted by the base. So if we write it that way, that is CH3CH2 twice NH2 plus we have to write, that is 1 H plus is added to the amine group of this, and the acid part loses its hydrogen, so it is left with CH3COO minus, and this is the equation which shows the acid base reaction wherein basic substance is accepting H plus from the acid. Fourth part is now diethylamine reacts with the ethanoyl chloride. Here it's given, complete the equation for this reaction. Now with ethanoyl chloride, let's understand what happens is it acts just like an acid, but here there is no H plus to get accepted by the amine group. So now what's going to happen is that it's going to react with the amine part to form an amide linkage, just like an amino polymers which happens, that is the amide polymers which we call polyamide. Similar amide linkage will be formed, that is the H from the NH amine group is released and the Cl from the ethanoyl chloride, that is acyl chloride, is lost as an HCl group, and the remaining 2 parts just bonds together. So if we join the remaining part, we are going to get the diethylamine part which directly bonds with the CO part. So I should write directly CO part here and then the CH3, that is N and CO. CO part here and the nitrogen gets bonded to form an amide linkage. So that's the linkage. and a small molecule is eliminated out, just like a peptide linkage or polyamide linkage. Amide linkage is formed. The C part is table 7.1 shows monomers that can undergo polymerization. So this is a monomer. Complete table 7.1 to show the type of polymerization. Now this is a monomer, and we can see that here we have CH2 and C having a COOH group. Now what does that mean? That CH2 have a double bond here and a CH3 group here and a COOH group here. Now if there is a C double bond C group here, that's going to make an addition polymerization, because double bond forms an addition polymer. So type of polymerization is an addition polymerization. With the second part here, we can say that there is an acyl group or carboxylic group and the alcohol group that's going to make an polyester kind of polymer, and that is the condensation polymer, because a small molecule is eliminated out, joining the monomers together. Again here we have a carboxylic part and NH2 group, which again forms an amide linkage to form the polymerization. So this is again a condensation polymerization. Addition is possible only when we have one C double bond C minimum to form that. So addition polymerization is just one, and the remaining two are going to form a condensation polymerization. The second part is ethane dioic acid, as given here, can react with the propane 1,3 diamine. This is the propane 1,3 diamine to form polymer W. Draw a section of polymer W showing one repeat unit to be shown. The new functional group formed should be displayed. Okay, as I've already said that when the carboxylic acid reacts with the amine part, an amide linkage is formed where the OH from the carboxylic acid and one of the H of the amine group is lost as water, and the remaining group joins. So if we are going to form a polymer, we have to remove the alcohol from both the carboxylic acid and one NH from both the amine group, which continues as a polymer. So if we draw directly the remaining part, then we directly have C double bond O, which is given here. Then again another C double bond O, which is given here. That is carboxylic part that directly joins with the NH group here. So this is the NH group here with the propyl chain in between, that is CH2, 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 and again the NH group here. So this is how it's going to form a polymerization, and you can see this is the one repeat unit. Now from here it continues as such. Again, that's it gets repeated. So this is how we are going to draw. As it says, the new functional group formed should be displayed. So here we have shown all the bonds of the new functional group, because the new functional group is the amide group formed here, that is CONH. So that has to be displayed fully. The remaining part, if you don't display fully, that's fine. So here the next part is polyalkenes biodegrade very slowly. Explain why. Now as we have already seen that polyalkenes are what? They have C double bond C, which then polymerizes continuously as such on all these sides. So the repeat unit is that C double bond C, which changes to one C single bond C. Now what happens is that if this undergoes biodegradation, this bond has to be broken. If these bonds are broken, then only it can undergo biodegradation, but this is not that easily possible, because the C single bond C bond is quite strong and inert, or you can say it's non-polar, so cannot be broken easily. So cannot be broken easily, and so it does not undergo biodegradation. that easy now. So here our question 7 ends. Let's continue with question 8. Now the A part says compound A is analyzed by carbon 13 NMR and proton NMR spectroscopy. Now here is the compound A which we can see here, and state the reference substance and a solvent that can be used in NMR spectroscopy. Now what is a reference substance? Reference substance is a compound which can show a peak, a very high and sharp peak, and which can be considered as zero. So that is called reference, and for reference we use tetramethylsilane. Tetramethylsilane, that's the common reference substance which is used because it has like a silicon surrounded by 4 methyl group, and it gives a very sharp peak at 0. Why? Because all the protons present are in the same environment, so it's going to just produce one peak, but that's going to be a very sharp and high, and so that's why it's called a reference peak. Now what's a solvent? Solvent is a substance, or you can say a solvent in which we can dissolve our compound, but the solvent which we use should not interfere with the peaks of the compound, so that's called a solvent here. So the commonly used solvent is CdCl3. Now what is D? D is deuterium, you know, the heavier isotope of hydrogen, and the deuterium does not produce any peak in NMR spectroscopy, so we use CdCl3 as a solvent. So here are the two substances. Now the B part is predict the number of peaks in carbon 13 NMR of spectrum of A. Yeah, let's have a look here. Now what are the different carbon present in it? Now let's have a look first. How many carbon do we have? This the 1, 2, 3, 4, 5, 6 and 7 carbon we have in this compound A, but we can see that the carbon here and here, these two carbon are in the same environment because they both are bonded to CH, which is further bonded to oxygen. So these two carbon are in the same environment, so it's going to produce just one peak. The remaining all carbon are in different environments. So out of 7 carbon, the peak which we get in carbon 13 will be 6 peaks. If we count again, then we can say this is going to produce one peak, second, third, fourth, fifth and sixth peak of all these carbons. So 6 peaks will be produced. Now the proton NMR spectrum of A shows peak in 4 different chemical environments. Complete table 8.1 for the proton NMR spectrum of A. Now let's have a look how many different protons we have here. Let me remove all this. So now if we see then how many proton are there. Here we have CH3, here we have CH, here only C is present, again only C is present, here we have CH2 and here we have CH3. So different protons which are present are 1, 2, 3 and this 4. Different protons are present here. These two carbon does not carry any protons, so it's not going to produce any peak. So now we have already mentioned these two carbon are in the same environment. Similarly, this 3 plus 3, 6 protons are also in the same environment and it's going to produce the same peak. Now let's see here, chemical shifts of different protons are given here in ppm. Yes, here, right? Now this is 1.10 and this is 1.50. Let's have a look at both of these splitting patterns, chemical shift, that what environment it can belong to. And also it's given here 6. Now if we have 6 protons responsible here, obviously these are the 3 plus 3 protons, which total ups to give 6 protons, and so 1.50 is the chemical shift which is produced by this proton. Now with them we know there is bonded CH. Now we know the splitting pattern is the number of protons on the adjacent carbon plus 1. So the proton which is adjacent to this 3 plus 3 protons is 1. So 1 plus 1, that is equal to 2. So splitting pattern for this 6 protons will be doublet, right? So here we directly write doublet for this proton, and the number of proton adjacent carbon atom is 1, that we have already derived. Now let's see 1.10 again is a similar chemical shift. Here we can see it 1.10, where it can be CH3, CH2 or CH alkyl or alkane groups bonded to each other. And so if we have a look here to the structure, then this might be the proton which produces the chemical shift in the same environment. And how many protons are there on the adjacent carbon? 2. So let's write for the same. So number of protons responsible are 3. Number of proton on the adjacent carbon is 2, and so the splitting pattern is 2 plus 1, that is triplet. Okay, yes. The next two chemical shifts are 2.85 and 3.75. Now how many protons are we left with? We are left with this proton and we are left with this proton. Now we know that this proton are adjacent to CO group and this proton is adjacent to only O. So let's have a look that what are the two chemical shift. It's 2.85 and 3.75. Now 2.85 is in this area, this range, 2.85. Now adjacent to it is CO, right? So let's have a look that adjacent to it, which is having a CO, it's this proton, that is CH2 is having CO adjacent to it. So number of protons responsible for that is 2. Now adjacent to it, it has C double bond O, but on the other side it has CH3. Let's have a look what is there. Yes, this is CH3 present besides this CH2 group. So then how many protons are on adjacent carbon? 3, and that's why the splitting pattern will be 3 plus 1, that is quartet. Okay, yeah, 3 plus 1 quartet, yes. And 3.75. Now 3.75, this 3.75 comes in this range, where we can see that it is the proton to which an oxygen is bonded just to the carbon to it. So oxygen is directly bonded to the carbon carrying this proton. So obviously we have already seen that in this here, this CH. Let me rewrite here CH. This CH group is having the carbon directly bonded O to it, right? So this is the only one proton which is responsible for this peak, but adjacent to it are 6 protons. We have already seen that this EH is bonded to 2 methyl groups, that is CH3 and then O. So on this side we don't have any carbon or no proton bonded to that carbon, but on the other side we have total of 6 protons. So 6 plus 1 will be 7, but then in that place we just write multiplate. Multiplate will be seen for this proton. So I hope this NMR question is very clear and it's quite easy also. Let's go ahead with question 9 here. The question 9A is the structures of amino acids serine and lysine are shown in figure 9.1. The two structures are shown with the side chains shown here. Now the remaining part of all amino acids are same. What differs is these two side chain in all the amino acids. So now draw the structures of the dipeptide serine and lysine with the molecular formula C9H19N3O4. The peptide functional group formed should be fully displayed. Now if you read the question, the serine has to be added first and then the lysine. So what I suggest is here we have serine and lysine, and if we are drawing a dipeptide for it, we just have to remove the OH and one H from NH2 group and just bond it together. So join it from this part. So removing it out a water molecule from both of this molecule and just joining. So let's draw it. NH2 is here, then CH2OH, that's the easiest part. Yes, here we draw, the H is drawn here, the C double bond O has to be fully shown because here it's written displayed the dipeptide, that is the peptide functional group formed. So here is that peptide which is formed, so that we have to display fully showing all the bonds. So here the NH, one H is removed out, so we have drawn one NH, and from COOH, OH is gone to form the water, so we have removed that. The remaining part, that is CO and NH, are shown here. This is the display formula of the peptide functional group form. Now the remaining amino acids of this lysine remains the same. So see here, CH2, 4 times the methyl group in between, and then the amine group, and here we have H and the COOH remaining. So this is how you're going to draw the dipeptide of serine and lysine. Very easy. Yes. In the B part, the isoelectric point of serine is 5.7 and of lysine is 9.7. Understand what is an isoelectric point. It is the pH at which, so here it's the question, state what is meant by the isoelectric point. So let's understand this isoelectric point and also write its definition, that it is the pH at which the given amino acid are having no charge, that is no net charge. That is, if it has one positive charge, there should be one negative charge on the amino acid, so as to make it an overall neutral or no net charge. So what is an isoelectric point? It is the pH at which an amino acid have no overall charge or no net charge, or you can even say it is neutral. Now the B part is a mixture of serine, lysine, and serine lysine, that is the dipeptide, is analyzed by electrophoresis using a buffer at pH 5.7. Now we know that at pH 5.7 serine exists as a neutral, so it has no overall charge. And here the electrophoresis diagram shows that this is the point at which the mixture is applied. So if here is the mixture applied and the charge shown, after some time amino acids which are negatively charged will move towards this positive end, and the amino acid which exists as positively charged, overall net positive charge, will move towards this negative pole. So there will be a movement of amino acids in the two different directions according to its charge. Now at isoelectric point of serine, we have seen it's already 5.7, and this electrophoresis is also happening at 5.7. So serine is not going to move, it's going to remain at the same spot. So it does not have any overall charge, so it doesn't move towards any of the terminal. So here is the question. Now draw and label 3 spots on figure 9.2 to indicate the predicted positions of each of these 3 species, serine, lysine, and the dipeptide after electrophoresis. Now if lysine exists as neutral at 9.7, then at pH 5.7, which is acidic for it, will make it overall positively charged. Now let's understand how the pH is acidic for it. Now if the pH is acidic for it, then this amine group, let's see on this lysine, this amine group is going to gain an hydrogen ion, H plus will be added to it to make it here NH3 plus. Now if that's going to make it NH3 plus, it's going to gain an overall positively charge, and so it will move towards the negative terminal. Now same thing will happen with its dipeptide also, because the serine part of the dipeptide will remain neutral, but the lysine part of the dipeptide will become positively charged, and so it will also move towards the negative terminal. But the problem is that out of lysine and the dipeptide is having an higher MR. It's heavier in weight, so it's going to move slowly, and lysine will move more distance. So let's label it here that this is the spot which will be produced by the serine amino acid. The next spot towards the negative terminal, it will be dipeptide. So here we can label dipeptide, or even you can label it as serine and lysine, the short form of the dipeptide. And more distance will be traveled by lysine, so you can just label it as LYS, lysine, to show that the amino acid lysine traveled more distance. So this is how you're going to make it. You can draw these two spots in any of the distance given here, right from this cross to the dotted line. In between these two dotted line you can draw anywhere, but yes, dipeptide should be closer to the center point and lysine should be closer to the negatively charged terminal. That's how you're going to take care. Now that we'll have to explain here, because explanation is asked, explain your answer. So we are going to give the same explanation that serine has no net charge at 5.7 pH, so it will not move, but at pH 5.7 the dipeptide and lysine are positively charged, so moves towards negative terminal, but dipeptide, that is serine lysine, has higher MR, or you can even write has a higher mass, so moves slower, or you can even write less distance. Okay, let's move to the next part here. The C part here, it says figure 9.3 shows the synthesis of compound R from compound P. Now here we have compound R given here. Yes, that's a cyclic substance with the COO group, that is the ester group here. And we have amine group also. Let's see what's the starting compound P here. P is given here again with a CONH group, that is the amide group, that is called amide. CONH group is called amide group. So we have amide group here. Yes, that changes to some compound Q here, and that Q is changed to R here. Now here draw the structure of Q in figure 9.3. Now let's understand what is happening to the P and then forms Q. Now if you have a look at the molecular formula, it is C6H3NO3. There are 3 oxygen, while in P there was only 2 oxygen and then nitrogen, and these have only 2 hydrogen. Okay, here the overall hydrogen is 13, but if you count hydrogen in P, then here we have CH3, CH here, then here is CO, so no hydrogen, 1 hydrogen here, we have CH2 here, again we have CH here and CH2 here, so 3 plus 1 4 and 2 6 and 7 and 8 9 and 10 and 11 here. So we need to understand that 2 hydrogen are added and 1 oxygen is added. So in short, water is added in P to make the compound Q. Now what is that? That is addition of water, that is hydrolysis, and on hydrolysis this bond breaks and the water is added. So we just have to break this bond and add the water. So starting with this portion, I'll start drawing. Yes, here we have ring. Here we have C double bond O. So that will change to COOH, that is the carboxylic acid. The remaining part of the ring remains same. So I'm drawing as such here, here, and here we have NH. But then that changes to NH2 because water is added here. So OH and H added here, making water adding here, and the hydrolysis happened because that bond is broken. So this is the Q compound. Now what happens in step 2? What we can understand is that the OH group here and the carboxylic acid here gets bonded together, where water is removed out to form an ester group here. Right, we can see that ester linkage here. So same compound again rebonds in a different way to form a linkage, and we can see that this ring, that the remaining part of the carbon here is shown here as a side chain. Yes, so draw the structure of Q. It's given here in 9.3 we have drawn. And the B part, sorry, the second part is state the reagents and conditions for step 1 and 2 in figure 9.3. So we have already seen that in step 1 hydrolysis occurs, and hydrolysis is done with the help of any dilute acid. We can write dilute H2SO4 or even dilute HCl will do. But only adding acid will not do, we'll have to heat and reflux also. So heat and reflux is also needed. And in step 2 we know we are rebonding in a different way. So again an acid is needed, but here we need a concentrated acid like sulfuric acid. So we write concentrated sulfuric acid, and again heat is required, but we don't need a reflux. Remember, when we have to do hydrolysis, that is breaking of bond, we need dilute acid along with heat and reflux. But if we are rebonding to form you can say a ester linkage and amide linkage, we need concentrated acid along with the heat. Now hope all my explanation is quite clear. Here our paper ends, and you can refer the other 2 videos for to watch the earlier questions in the same paper.